Good morning, everybody. My name is Patricia Peralta. I work at the Hamburg University of Technology, and I'm going to present you a little bit about our automated defect detection process in clay printing. So first, we have that the AEC industry is facing several challenges like labor shortages, increasing design complexity, and also increasing cost and time in construction. And now there's efforts to use additive manufacturing to face these challenges and also to address towards the more like sustainable construction. There's also a new open research field that is the concrete printing. So in concrete printing, we have a more eco-friendly material. We also have an increased productivity and customization, as well as a reduced weight compared to the traditional earth construction processes. But we also encounter several defects during printing, as the previous presenter also pointed out. So here we can explore some synergies with concrete printing, since we observe very similar defects, right? We have tearing, we have sagging, and we can also have cracking during shrinkage. So with this, we define the research gap that we have these defects that usually affect the structural integrity, the load-bearing capacity, and the overall durability of the concrete printing structure. So even though there are some research in defect detection, usually it's for fused filament fabrication, or in a very limited efforts in concrete printing, but there's not much research in clay printing. And in particular, we have a lack of data sets to be able to develop these defect detection models. So for this, we propose the automated defect detection preprocessor, which is a tool to build data sets aiming to support these defect detection models. So our defect detection model is developed based on a research methodology proposed in a previous study. It was developed for fused filament fabrication, but overall, we're gonna adapt it to clay printing. So we have two main phases for it, the data preparation phase and the classification model development phase. So our main focus will be in the data preparation phase, where we're gonna have the data collection, we process the data, we add the labels to it, then we augment the data to be able to have more robustness on the model, and then we split it into three different data sets, into a training data set, a validating data set, and a testing data set. And then we switch to the next phase, where we pick the architecture, the hyperparameters, we train the model, and if we're satisfied with the accuracy, we have already our classification model ready for use. So for the ADD preprocessor, the main idea is to collect and standardize images from different sources, also to be able to label this image data. We have labeling strategy where the defects are manually annotated using bounding box and labeled according to index numbers, as we show here. And we also consider requirements for image size. So here we want an image that is big enough to prepare, to provide the context for proper defect detection, a color bright model to reduce the variability due to material color. Also, we have to consider the design intent when we're labeling defects, because sometimes the structures have details that have a functionality that may be confused with a defect. And we also have to consider data augmentation, because besides that we have a very limited size of data set, we also need to improve the robustness of the model. So our tool is implemented using Python. We develop a GUI for the manual user inputs. where the users can select area of interest and do the labeling process. And we also have processing algorithms that will resize the input images to the desired size. We also convert the images to the grayscale, and we perform the data augmentation using the mirroring technique, adding noise, adjusting the brightness, and also changing the rotations of the images. For validating our tool, we develop a proof of concept where we're going to generate a database from images collected during experimental testing under laboratory conditions. And these tests, we were testing 6 different clay mixes for printing. So we were expecting a lot of defects during the printing process. We used a high definition camera to collect the images. So we had enough room to select our areas of interest. And at the end, we selected 16 images for testing the ADD preprocessor, where we have 5 images for buckling, 3 images for sagging, 1 image having tearing, and 7 images with no defects. So for generating the data set, first, we have to adjust the image size. So for this, we select our area of interest, and we cut it to the right image size that we selected. That will be 640 by 640 pixels. Then we applied the colorblind model. So we adjusted the grayscale. When we proceed to labeling the defect, where we provide the bounding box and we also the corresponding index number. And then we perform the data augmentation. So for processing, first we mirror the image, then we rotate it between 20 plus minus 20 degrees. And we adjusted the brightness besides adding noise to it, so we can consider different lighting conditions. So at the end, from 60 images, we generated 64 images, where we're going to have positive instances and negative instances, providing a more robust data set. As a conclusion, we have that the defect detection in clay printing has been hindered due to insufficient data. So we need more data to, 1, know the defects that are being present in clay printing, and also for be able to detect it. So we designed the ADD preprocessor tool for generating the data sets to support these detection models, where we created an image data, transform it to a standardized data set that meets the requirements for deep learning-based defect detection models. And the results showcase the potential of the ADD preprocessor to address the lack of data sets that hopefully will help us to develop more approaches to autonomous defect detection in clay printing. And as a future research, we would like to apply it for real-time defect monitoring during printing, and to also test different more advanced neural network architectures like transform-based models. Thank you very much for your attention.